This video is meant as a review of the basic exponent laws as well as negative exponents and fractional exponents towards the end. When somebody talks about a power, they're talking about the whole structure here. The power is made up of two numbers. A larger number we call the base, and then a smaller number up high known as the exponent. And really, back in mathematical time, what happened is somebody got fed up with having to write out the expanded form. And so at some point in time, somebody said, you know what, when I have this same number that is going to be repeatedly multiplied by itself, let's make a shortcut. We'll make the big number the number that gets repeatedly multiplied, and then this little number up high, let's call it an exponent, tells us how many times to multiply that same number together. And so it's a shortcut. And if you are asked to evaluate, then you are asked to give the rock solid answer to this. This would be simplified exponential form. This is expanded form, asking to be evaluated. Here we've got 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. So the evaluated answer is 32. Now, again, another set of shortcuts. We have learned when to add, subtract, and multiply these exponents as a shortcut to having to write it all out. The first two basic exponent laws that we learn, multiplying powers, if I have 2 to the exponent 5 times 2 to the exponent 3, or 2 cubed, then that really means this 2 multiplied by itself 5 times for my 2 to the exponent 5, multiplied again by itself 3 times, and so overall I have 5 and another 3 2's. I have 2 to the exponent 8, and we can easily see that when we write it out. And so when we decided to, I don't want to have to write that all out all the time, we've got this shortcut that if I have powers of the very same base and I am multiplying them, I get to add those exponents. Our first shortcut exponent law. And so our first shortcut exponent law would say, okay, if you've got the very same base, you've got 5 of them from the first product multiplied by another 3 of them, we get to add those exponents for 2 to the exponent 8. And in general, you'll see a lot of textbooks where they represent the base as an A and the exponents as M and N. And my first multiplying powers, we get to add those exponents. Similarly, we've got this second shortcut where we divide powers. And if you remember, we get to subtract these. But why do we get to subtract them? Well, it comes from what really happens with this. If I have my powers written out in expanded form, I would have 2 to the exponent 5 divided by 2 to the exponent 3. And so we know that 2 over 2 is 1, and 2 over 2 is 1, and 2 goes in here once, and 2 goes in here once. And in the numerator, I have a 2 times 2 left. In the denominator, I just have 1 times 1 times 1 left. And so the simplified exponential form, I would have 2 to the exponent 2. And of course, we can show that we get that if we subtract those exponents. Now, subtracting those exponents will, in this case, get us a 2 to the exponent 5 minus a 3, getting us that 2 to the exponent 2. But this particular exponent law can run us into a couple of problems. And so problem number 1, from the idea of subtracting these exponents, comes from the fact that we can get negative exponents out of this deal. Because what if I had 2 to the exponent 3 divided by 2 to the exponent 5? Well, again, if we expand that out, I would have 2 multiplied by itself 3 times in my numerator, 2 multiplied by itself 5 times in my denominator, and if I do my canceling here, 2 over 2 is 1. How many 2's in a 2? It's 1. 2 goes in here once and in here once. And in the numerator, I get 1 times 1 times 1. And in my denominator, I have my 2 leftover 2's, so 2 to the exponent 2. However, if I take that shortcut exponent law that we wanted so that we didn't have to write it all out, I would have this 2 to the exponent 3 minus a 5. And that results in a symbol that has absolutely no mathematical meaning. Take a 2 and multiply it by itself negative 2 times. Well, that doesn't have a logic to it. And so I try to remember that this is just code for the fact that if you get a negative exponent, it means you did have some extra leftover 2's, but they were not up here in the numerator. They were actually down in the denominator of this fraction. So it's code for being in the wrong spot, wrong part of the fraction. So problem number 1. Problem number 2, with wanting a shortcut exponent law here for subtracting fractions, comes with something like this. What if I had 2 to the exponent 3 divided by 2 to the exponent 3? Well, if I expand that out into expanded form, we would have 2 times 2 times 2 in the numerator, 2 times 2 times 2 in the denominator, and we can easily see that all these 2's cancel out to a 1 times 1 times 1 in the numerator, 1 times 1 times 1 in the denominator. I truly do have the same thing over itself, and so that makes a 1. However, if we use our shortcut exponent law, I get my 2 to the exponent 3, subtract a 3, and that gets me this 2 to the exponent 0, which again means nothing mathematically. Take a 2 and multiply it by itself 0 amount of times. Why is that a 1? Well, it's a 1 because if you want shortcuts, you're going to get glitches. Negative exponents are glitches of this shortcut of subtracting exponents. We just have to remember that means, hey, I had more of my powers in the denominator, and so I do have 2 leftover 2's, but not in my numerator. They are in my denominator. The extras are downstairs. When I get this exponent 0, it just means that it would have come from a situation where I had the same number of multiplications of my base on the numerator and the denominator. And so again, I think of it as code. A 2 to the exponent 0, 0 is code for, oh, it came from a situation where I canceled everything out, the same thing over itself. And so we've got our set of general exponent laws here that if I have powers of the very same base and I am dividing them, I get to take that same base and subtract those exponents. However, if I find that that subtraction results in a negative exponent, that simply means that my powers are down in the other part of the fraction. And if I get a to the exponent 0, that is always going to work out to a 1. Those are our 2 basic exponent laws and how they can run into troubles. We can expand those exponent laws to include power of a power, power of a product, and power of a quotient. Power of a power just means repeatedly multiplying a power. And so if I have 2 squared all cubed, when I have an exponent on a bracket, that truly means take that bracket and everything in that bracket will multiply by itself, in this case 3 times. And if I truly expand that all out, I'd have 2 times 2 in each of those brackets. And so when we do expand it out, we can see we have 6 of those 2's repeatedly multiplying. And so again, we like our shortcut exponent laws, and so we shortcut this one just to remember that if we have power of a power, then I get to multiply those exponents. So that 2 to the exponent 2 to the exponent 3 means that I am allowed to have 2 with a 2 times a 3 in my power, so I can see that I am repeatedly multiplying 2 by itself 6 times. So in general, my exponent law here, when I have power of a power, my exponent is involved with multiplying the exponent inside, mn. All right, power of a product. So I have a power of several things multiplied together, a product. And so this one is one that causes some trouble with what I call silly glitchy errors, where you just forget. Almost everybody will multiply this 2 and 3 and say that the y has an exponent 6, but it's important to remember that everything in that bracket is subject to that exponent 3, because truly what this is asking me to do is to take that same bracket and multiply it by itself 3 times. So I have this negative 2 in this bracket multiplying 3 times. I have an x in each one of the bracket multiplying by itself, and I have a y squared in every one of the brackets. And so truly what's happening here is we have a negative 2 cubed, we have an x cubed, and a y squared, y squared, y squared means I have y to the exponent 6. If I was to evaluate that, we would have 3 negatives here, making this a negative 8x cubed y to the exponent 6, but this can be left in simplified exponential form. And so in general, my power of a product is similar to the power of a power, but just remembering that with this negative 2x to the exponent, 1, if it's not there, it's assumed to be a 1, y squared and all cubed, I simply have to remember that that 3 is multiplying inside each of those individual items in the bracket. So I have my negative 2 cubed, my x cubed, and my y power of a power here to the exponent 6. And so my general exponent law for that is AB as my product to the power m, a to the exponent m, b to the exponent m. Each of those items in the bracket are subject to that exponent. Similarly, power of a quotient. A quotient is the answer to a division question. Here I've got 2/5 to the exponent 3. And so truly again, when we write it out and expand it, we can easily see why we do what we do with these exponents. But I have 2 to the exponent 3 in the top because I have a 2 times 2 times 2 in my numerator, and 5 to the exponent 3 in the bottom because I have 5 times 5 times 5 in the denominator. And so my power of a quotient, shortcut law, means that I can take my 2/3 in my bracket and any exponent that is subject to the entire bracket. And this is why it's so important to put brackets on your fractions, because without those brackets, my exponent 3 would only be affecting the 2 in the numerator. But with the brackets, my exponent 3 is actually affecting the entire fraction. So I have the 3 on my 2 and the 3 on my 3, and I distribute that exponent into both parts of the fraction. So be very, very careful with your exponent brackets. This, exponent 3 means 2 cubed over 5 cubed. It is not equal to, down here, my 2/3 cubed. That would just mean I would have, here I would have an 8 over 125. Here I would have 2 cubed, which is 8 over 3. Your brackets very much matter with your power of a quotient. And so when I have any fraction to an exponent, we have a to the exponent m over b to the exponent m. And those are the basic exponent laws. However, we do in grade 11 head into a new symbol in the exponent, a fraction in the exponent. And if we would cover up the bottom of that fraction, it wouldn't be confusing at all. And it's just exactly the power that we're used to seeing. 4 to the exponent 1 is just a 4. But when we put a denominator in the exponent, again, it's just code. It's code for this idea of taking the root of a number. And so 4 to the exponent half is asking for the second root. We more commonly call it the square root of 4. And that's just asking, hey, what number multiplied by itself 2 times results in a 4? And so, of course, the square root of 4 is 2. We can also call for different roots other than the second root or the square root. Of 8 to the exponent 1/3 is asking for the third root of 8. What number multiplied by itself 3 times gets me this 8? And of course it is a 2 as well. A 2 multiplied by itself 3 times is my 8. So the third root of 8 is my 2. If I have a variable to the exponent 1/5, that would just be asking, hey, I have this mystery number, and once I know it, I'm going to ask myself what number multiplied by itself 5 times. And so we've got a new symbol up in an exponent. We've got a fraction, just reminding us that the denominator of that fraction is calling for a certain root of my base. I can have an exponent that represents multiple mathematical ideas. Here I have my regular power, 8 squared, but when I ask for an 8 to the exponent 2/3, I'm asking for a third root and a second power. Now, we can do this 2 ways. It is always easier to take the third root of a base and bring it down to a small number and then exponentiate it up, because the third root of 8 is a 2 and my 2 squared is a 4. It's much harder mentally, certainly on a calculator it doesn't matter, but if we're going to do these mentally, I can also take 8 squared and take the third root of that. 8 squared is a 64. And what number multiplied by itself 3 times gets me 64? Well, we get to that 4 in the very same way. But when you're mentally doing these, remember to take the root first and then the power second, and you get to your answer quite a bit more easily. Now, I call this a very bossy exponent. This exponent is calling for 3 separate mathematical ideas. This negative in the exponent has nothing to do with the negative out front that would mean below 0. This negative exponent, if you remember, is simply code for the fact that, yeah, I have some 8s left over, but not up here in the numerator of my fraction. This set of leftover 8s was down in the denominator, and so I simply transfer it down into the denominator and change that now to a positive exponent, indicating that it's in the proper part of the fraction. So, again, we'll take the third root of 8 first, the second power. The third root of 8 is a 2 squared, and so I get a 1/4. Probably the most difficult fractional exponents come when you've got a fractional exponent on a fractional base. However, we can think of this, I guess, in 2 ways. I can take the whole 4th root of both of those numbers and think of it as a set. The 4th root, what number multiplied by itself 4 times gives me 81? Well, that's a 3. And what number multiplied by itself 4 times gives me a 16? That's a 2. If we think about our power of a quotient rule, we can also recognize that I can distribute that quarter into my fraction so that it is subjecting to both the numerator and the denominator, and we'll get to our 3/2 by looking at the roots separately. Either way is good mathematical form, and we get our 3/2. Probably the bossiest exponent of all is one that calls for a regular power, a cube, and a directional, putting everything into the proper part of the fraction, as well as a root. When I have a multiple bossy exponent here, I like to tackle it in parts. I like to get rid of this negative exponent first. Now, we can think of this in a couple of different ways. Probably the easiest way is similar to this situation, thinking about putting that 3/4 in on each of those parts of the fraction. If we do that, we now recognize that they're both in the very wrong spot. My 81 does not belong up here. My 16 does not belong down here. And so code tells me that I'm in the wrong part of the fraction here. And so I put my 16 upstairs, my 81 downstairs, and now they are in the proper part of the fraction. If I take my 4th root of 16, that's a 2 cubed. 4th root of 81, that's a 3 cubed, and I get to my 8/27. Once you recognize that if I put this on both of my numerator and my denominator, and they will be both in the same spot, most people very quickly get to the shortcut of realizing to take care of this negative exponent. If I was to put the negative exponent into that bracket, it just means that these guys would be in the wrong spot. And so flipping the fraction means that I can then think of it as a positive exponent now, because if I distributed the negative in, I would put them both in the wrong spot. So let's put them back where they belong, 16 over 81. And then I could take the fourth root of 16 over 81 all cubed. And so I would have my 2/3 all cubed. And then, of course, my cube, my power of a quotient, I would be cubing the top and cubing the bottom. And that, in a nutshell, is a review of all of the exponent laws that you will need as prior knowledge going into our logarithmic function unit.